So we'll start today with the describing function analysis method. Describing function method. So we can use the describing function analysis for analysis of nonlinear systems, just like we use the transfer function method, which is actually a frequency-based approach. We can apply the describing function analysis. Uh, in this case, we'll be using the Fourier transform for analyzing the frequency response behavior of these systems for analysis of nonlinear systems. So uh, there'll be a number of things that will cover up during this uh, while studying describing function method. To sum it up, we basically have a normal linear system described by a function g of s. We understand the behavior of the system for an applied input r and an output y. We understand the behavior of the system, but because of the presence of now some nonlinear element in the system, or naturally when occurring most often, there will be a nonlinear input that will be nonlinear behavior that will be describing that will be actually acting upon this system. So how to find the describing function for nonlinear elements? Uh, this will be what we'll be looking at is how to find the behavior of this nonlinear system. That, in other words, is by finding out the describing function for this system. So this nonlinear element as present here, how to find its behavior, and particularly if this is a hard nonlinearity. Fine. We have discussed about soft linear nonlinearities and hard nonlinearities. So if it's a hard nonlinear system, that means we cannot linearize it. That makes it even more complicated. A soft nonlinear system has the property to be linearized. So we could have simply linearized the model and got this and solved the behavior, analyzed the behavior of this particular block diagram. But if it is a hard hard nonlinearity, saturation, hysteresis, extra, or a combination of these, we need to understand, we need to find out a function that basically determines the behavior of this element so that we can determine the behavior of this overall system. Uh, so once we do that, we'll be able to describe the dynamic behavior of the system. So herein we need to find out the hard describing function. Now we have done the phase plane analysis, but using the phase plane analysis we can only check the behavior of at most second order systems. We can go beyond second order systems by breaking them down into second order systems, but becomes very complicated for phase plane analysis to describe such a behavior. As well as its most of phase plane analysis only gives us a graphical representation of the system. It will not help us analytically solve, give us a function based response, function based output response of the system, so that we can determine the behavior of the system for all values of time t. So here the describing function method is much more useful for nonlinear systems. We can get a complete equation of the system. We can check whether how the hard nonlinearity is behaving in the system and analyze for different properties. Fine. So once we have the describing function, we can analyze the stability of the nonlinear system by extending the criterion for linear systems such as Nyquist criterion or Routh's criterion. Right? So we can analyze for stability. So generally speaking, Nyquist criterion is extended in case of a describing function method. It is actually based upon the Nyquist criterion of analyzing and solving system behavior. So these things will be covered in this topic of describing function methods. There are some assumptions that will be making, that will be taken into account while while determining the describing function for any nonlinear element. So the assumptions that we'll be making for analysis of a nonlinear system using the describing function method will be: the input of the nonlinear element will be a sinusoidal signal. So it will be a sinusoidal signal. That's fundamental components of the output actually. So this in other words means the fundamental component of the output contributes to the system response. So this is also understood from linear system behavior that we have already analyzed. Most of the linear systems have a low pass filter characteristics. So this is something you should remember. Linear systems mostly have low pass filter characteristics, and that means higher order harmonics will be eliminated in the system, and only the lower order harmonics will be playing a role. That's actually the fundamental components of the output will be contributing to the system response. Secondly, the non-linearity is actually small. They won't be having larger magnitudes. Therefore, the harmonics are even smaller in amplitude. So the behavior, the nonlinear element in the system will actually introduce harmonics in the system. But since the magnitude of these nonlinear elements, contribution of these nonlinear elements is very small, so we can, in other words, say that the harmonic contribution of such systems is even smaller. Fine. Thirdly, we'll be assuming that there is no time varying characteristics. We will assume that a nonlinear system is not varying with respect to time. The parameters of the system are not varying with respect to time. It's a time invariant system. So these are three assumptions that we'll be making. One, the input of the nonlinear system will actually be a sinusoidal function. Fine. So one will be deriving the describing function of various nonlinearities that we have discussed, mostly the hard nonlinearities. We'll be assuming that the input in all the cases will be a sinusoidal function. Accordingly, the describing function will be determined. As in case of linear systems, we are mostly concerned with the step input. Here we'll be focusing on the sinusoidal input. Secondly, since the nonlinearity in itself is small, the harmonic contribution of the nonlinearity will be even smaller in amplitude, so we can actually uh, neglect them in some cases. Fine. And thirdly, it's a time invariant system. That is, no time varying characteristics will be included in this nonlinear element design while determining the describing function. So now coming to the definition of a describing function, it's again a ratio defined by we use the symbol n for describing a describing function of any system. Uh, so it's a ratio and equal to fundamental component of output of nonlinear element divided by the sinusoidal input to the nonlinear element. The fundamental component of a nonlinear system, fundamental component of the output of the nonlinear system, you are not taking all of the output, will only be concerned with the fundamental component of the nonlinear uh, of the output of the nonlinear element, and over the input, that is the sinusoidal input in this case. So again, it's a ratio of output to input, but the output is only the fundamental component and the input is the sinusoidal input, and it is shown as y1 angle phi 1. That's actually referring to the fundamental uh, magnitude and phase of the output divided by x, where phi 1 is actually the phase angle of y1, x is only referring to the amplitude of sinusoidal input, x is referring to the amplitude of sinusoidal input, y1 is referring to the amplitude of the fundamental component, and phi 1 is the phase angle of y1. Fine. So that means for an input xt equal to x of sine omega t, the output may be expressed as the Fourier series expansion. Therefore, for an input xt equal to x sine omega t, for any nonlinear element, if we are applying an input of x sine omega t, and this is your nonlinear element here, yt will therefore be can be determined using the Fourier analysis: y1 sine omega t, y3 sine cube omega sine 3 omega t, sorry, y5 sine 5 omega t, and so on. So it will be the Fourier analysis that will be used in case of the describing function method to find out the output. So in other words, we can therefore write y omega t equal to, as we know from the Fourier analysis, fine. So we are actually applying a sinusoidal input to this nonlinear element. Since this nonlinear element has, as we have also done in harmonic analysis, this is contributing to various harmonics. So output will be output will be considered. Output will be summation of the various harmonic components: the first harmonic, the third, the fifth, the seventh, so on. Um, and we cannot actually neglect after some magnitude. So these can be then represented by the Fourier series as a naught summation of n to 1, n equal to 1 to infinity a n cos n omega t plus b n sine n omega t. Fine. A naught plus summation n equal to 1 to infinity yn sine n omega t plus phi, where yn is under root of an square plus bn square, and phi n is tan inverse of an by bn. तो ये जो आपकी इक्वेशन है, we'll be using this equation, these two equations rather, to find out the output response to any sinusoidal input of any nonlinear system, where you know basically a and b, a naught and bn. I hope you remember the formulas. A naught is simply 1 by t, 0 to t. A naught is 1 by t, where t is time period, 0 to t, ft dt. An is 1 by t, 1 by pi 0 to 2 pi 2 by t rather 2 by t f 0 to t f t cos n omega t dt fine, and d omega t, and thirdly bn is 2 divided by t 0 to t ft sin n omega t d omega t. Fine. So you have also for an odd function and for an even function what is the values of a naught, a n, and b n. Fine. Where a naught is 0 and a n is a naught and a n is 0 and b n is 0. So now we'll be going to finding out the describing function for various nonlinear elements. So let's start with describing function of an on-off nonlinearity. So if we look at the characteristics of an on-off nonlinear system, so your output input characteristics will be varying between minus m to plus m. Now assuming xt equal to x sine omega t, the input is a sinusoidal function. We need to find out the output response of the system. So accordingly, as you can see from this behavior, yt, which is your output actually, to an input of xt. Right? So you need to find out yt for a sinusoidal input. So y of omega t is varying for between plus m for 0 to omega t to pi, and y of omega t is equal to minus m for pi omega t to 2 pi. Right? This is your on-off nonlinear element. This is your on-off nonlinear element. You are applying a step input to it. You need to find out what will be the value of y. Fine. So what you are actually doing is you are applying a sinusoidal input to it. And you need to find out what will be the value of y. Fine. So actually using Fourier analysis, you will actually come up. You will see that your output will be a square waveform. ठीक है. So अगर आप एक जिसका जो fundamental component होगा, that will actually be a sinusoidal waveform. Fine. So y of omega t has a max at it will be from 0 to pi. It will be having the value of m, and from pi to 2 pi it will be having a value of minus m. So this is the actual output of the system. This is not the fundamental component of the system. We need to analyze it using the Fourier transform. So furthermore, if you look at this behavior of y of omega t, it is an odd function. Fine. And also has a half wave symmetry. It is symmetrical about the after half wave 0 to pi के बाद जो response है, that is actually getting repeated. So y of omega t it is symmetrical about the half wave. So y of omega t can be set to be equal to y of minus omega t plus minus pi. Now going for the Fourier analysis for fundamental component of output. We are only concerned with the fundamental component y1. A1, A0 and B1 will actually be 0 for an odd function. B1 will be equal to 2 by pi. Time period here is only pi. 0 to pi y omega t sine omega t d omega t. Okay. So this is equal to 2 by pi. 0 to pi आपका minus m cos omega. Y 0 to pi it is m. Integral of sine omega t is minus cos omega t. So minus उसका 0 to pi are the limits. Applying these limits, we will get 2 by pi minus m minus 1 plus m cos 0, that is ये आपका b1, which implies b1 will be equal to 4m divided by pi. Fine. So you have an on-off non-linearity that's actually having the characteristics like shown in the figure. You are applying a sinusoidal input to it. You want to find out what will be the output behavior of this system, and for that we need to go for the Fourier analysis. We have found out the value of B1. So from here ये तो आपका magnitude and so y1 can be represented as summation a0 plus an plus summation of 0 to 1 है खाली, क्योंकि हम खाली we are concerned with the fundamental input. So it is equal to b1 sin omega t. a0 plus an आपका 0 है यहाँ पे, plus summation भी आपका cancel out हो गया because we are only concerned with the fundamental component. So b1 is 4m by pi sin omega t. So this is the value of y1, 4m by pi sin of omega t. And if you want to find out the phase of this system, phase you know is tan inverse of a1 by b1. Since a1 is 0, this will be simply equal to tan inverse of 0, that is actually tan inverse of 0 infinity. Right? The describing function, therefore, now for this system, n will be given to us by y divided by x, where y is the magnitude only, so 4m divided by pi, angle is angle 0, 4m divided by x, so equal to, that means it is 4m by pi x. So this is your describing function of this on-off non-linearity. Fine. So this is fairly simpler case. So we'll continue with deriving the describing function and describing function of various functions. In other words, you can also say this actually, if you plot n versus m by x, fine, so you'll get a straight line with a slope of 4 by pi. Okay, so n is equal to, this is simply y is equal to m. Okay, so it is a straight line where m is your slope. Talking about straight line equation, y is equal to m, वहाँ पे small m है, so यहाँ पे अब आपका वो slope 4 by pi है, and आपका जो x है that is actually your x axis is given by m by x. So we'll be actually plotting these curves, n versus m by x curves, right? Where n initially was the magnitude of the on-off non-linearity. Okay? So on-off non-linearity can have magnitudes. The magnitude may vary for different non-linear systems. जैसे भी आप basically you can introduce it in the system in a different ways. We'll continue with this next